Okay. But don't worry. Good. All good. Okay. So we were discussing traffic parameters, right? Traffic beta parameters. Two types. What? Traffic parameters, not the hardest.
Macroscopic.
Yes.
And another microscopic.
Another microscopic, very good. Macro and micro. Okay. And which one we are discussing? One. MSCR. Macro. Okay. And from macro, which one we are discussing?
Listener.
Huh?
That's just the listener.
Huh?
Listen motion.
He made many classes when he was attending. Now he's finishing up. Yeah, which one we are discussing from macro? Volume. Everything we had up to now was volume. Volume is per vehicles per unit time, right? And the time can be less than 1 hour. We call it what? Flow. Oh, okay. And
volume.
Huh?
Volume for 1 hour.
1 hour. We call it hourly volume, right? And where do we use it? Design. Okay. And per day, where do we use it? Daily volume. For planning, documentation, reporting. You are registered or you are also listening?
No.
My friends told me and he sat down that we can be a listener from our office. Okay. Because I talk so long. So. Okay. So now what discussion you were having in this example? This was about flow and flow rate. What were we trying to prove here? What was the aim of this, looking at this example?
How many vectors were last section?
But what were we trying to prove? What is the result we came up with in the end? It was something related to flow and flow rate. What is this showing? What is this table showing?
Related flow, flow, and partial time.
Sorry?
Cumulative flow in 50 minutes.
Okay, and what else? What is this last problem?
Last we say we have a problem.
Yeah, what was the problem is because of?
We have capacity.
The flow. We can get the flow from.
Now, what was the problem?
It will affect in the design.
The last one. Huh?
It will affect on the design.
Okay.
If we don't consider it very well, it will affect on the design.
It will affect, what will affect our design? The flow, the sub-hourly flow. Okay. How the flow changes between different intervals of the hour. So we are still talking about the same hour. Okay. But the flow is changing within the hour. If you do not consider this change, even if you take the volume as it is, it will affect your design. Okay. The volume is same as what we have. Okay. But we still have to see how this volume is divided between 15 minutes interval. Okay. To consider this aspect, we include a factor in our design which we call as the peak hour factor. Okay. So wherever you will see an equation for design, you should see this factor. Somebody says I designed a highway, I designed a signal, and he says I did it. Okay. And this is the design. And you ask him what is the peak hour factor, and he says I don't know it. Then you tell him what?
You are not engineer.
Huh?
You are not engineer.
You are not engineer. Very good. Come on. Okay. So peak hour, without peak hour factor, if you design something, it will not be effective. Okay. So how do we calculate peak hour factor? This is the equation. Okay. We need two things. V, capital V, which is hourly volume. Okay. And then we need this small VM15. Okay. We need hourly volume, and this is small VM15. What is small VM15? A small v is for flow or flow rate. A small v is for flow or flow rate. Okay. Capital V is for volume, because volume is for 1 hour, right? Bigger time. Flow is for less than 1 hour, so we use small v. Okay. Just so that you remember. And M is for maximum. M stands for maximum. Okay. So now you can see here we have different flows, right? Which one is maximum? So this is my VM. Okay. And why we are putting 15 here? To fix it. Okay. Because flow can be anything less than 1 hour. Okay. So you may take flow for 10 minutes. You may take flow for 15 minutes. And both of you will calculate peak hour factor. You may get different value, you may get different value. Okay, so we don't want this to happen. So we fix it. Okay. So for peak hour factor, the flow should be taken for 15 minutes. Got it? Okay. Now I need hourly volume and I need the maximum flow. So what is my hourly volume here? If I want to calculate peak hour factor for this example, 4,200. Okay, the total of the full hour. Okay, so this is my capital V, and what is my small VM15? 1,200. Okay, so if you take these values, then the peak hour factor comes out to be 0.87. Okay, you can check it. Now, peak hour factor has a range. It has a range from 1 to 0.25. 1 is the maximum, 0.25 is minimum. Now, if you look at the equation, when will I get 1?
When the V, the small equal.
When the V is equal to what?
4.
And what do we call this? 4 multiplied by flow. What will it become? No.
It will be
You just
equal.
listen. Don't talk.
Equal. Between the equation equal.
If flow of 15 minutes is multiplied by 4, then it becomes what? What do we call it?
Consider the hour.
Hourly volume.
Maximum flow rate.
Huh?
Maximum flow rate.
We call it flow rate. Okay, yeah, we are taking maximum, so maximum flow rate. But any flow of 15 minutes multiplied by 4 is flow rate. Okay. So, when the full hour volume is equal to maximum flow rate. Okay, VM15 is flow. When you multiply by 4, it becomes flow rate or rate of flow. Got it? Clear or not? Okay. So when full hour volume is equal to the rate of 15 minutes, the flow rate of 15 minutes. Okay. So whatever is happening, whatever rate you are getting out of 15 minutes, it's the same for the full hour as well. Got it? Okay. This was the full hour, right? And this is the rate from 15 minutes. So rate of 15 minutes, rate is equal to the actual volume. Okay, so whatever happens here in 15 minutes, it is happening with the same rate in the whole hour. This is what it means. Got it? Okay, the minimum of peak hour factor is 0.25. 0.25 means 1 upon?
No.
0.25 means what? 1 upon? 1 upon 4 is 0.25, right? Okay. Now when will you get 1 upon 4 here? When what becomes equal to what? Huh?
What? In the V.
V equals to?
V equal what?
Equals to 1. V equals to 1, it will be 1 upon 4 V. Huh?
If
What is minimum? Minimum is 0.
V15 equal to
This is where you entered. Huh? Okay.
when V, small v, equal to volume,
Yeah.
we can go to 4.
Yeah. Okay. When hourly volume equals to flow, not flow rate. For one, it should be equal to this whole thing, right? This whole thing is flow rate. Okay. So when V equals to this, only this, then you get 1 upon 4. Okay. Now what does it mean actually? So you are standing on the highway for 1 hour. In 1 hour, you were counting vehicles, but the vehicles only came during 15 minutes. The remaining 45 minutes, 0 vehicles. So whatever you have in 15 minutes is the same you have in 1 hour. Got it? Clear? So this becomes 1 upon 4. This and this equal, so this becomes 1 upon 4. 1 upon 4 means 0.25. Okay? Got it? Now what about traffic variation? If you get a value of 1, okay, that means what? Volume is equal to the maximum rate. Okay? So is there a variation or not in traffic? There is no variation. All 15 minutes are almost having same. Okay? This is how you get 1. So higher peak hour factor means variation is less. Okay? When traffic is consistent in 15 minutes intervals, then the peak hour factor will be higher. The variation will be less. Got it? Okay, and the other way around. The other way is basically easier to understand. 15 minutes, all vehicles. The remaining 45 minutes, 0. See? So much variation. Okay? So the peak hour factor is low. So when variation is high, peak hour factor is low. Okay? And vice versa. Okay, these are some values given for different areas, urban areas and rural areas, recommended values of peak hour factor. Okay, and last time I showed you the values for K and D factor, right? Urban area, rural area, suburban area. Okay, you don't trust me. Don't trust me, huh? Okay, but I told you what is the best thing to do? What is the best thing to do? I have these values. But, do it yourself. Find out your own values. These are just recommended values. They may work, they may not work. Okay? So, urban areas have more, rural areas have less. Right? Which one has more traffic variation? Urban?
No.
What did you just say? Variation is less. Peak hour factor is high, variation is less. Got it? Okay. This was this entire discussion, volume, daily volume, hourly volume, flow rate, peak hour factor was about one macroscopic parameter, which is volume. Okay. Now we will move on to the other microscopic parameter, which is speed and travel time. Okay. Now speed and travel time are considered together always in traffic engineering. Why? Because speed equals distance over time. Okay, so they are linked, they are not separate. Okay, so even later on when you will discuss speed data, you will also discuss travel time data. Okay, so they are interlinked. Okay, what is travel time? The time taken by vehicles to go from one point of the highway to the other point of the highway. Travel time, simple, right? Okay. Now we are discussing speed as macroscopic. Okay, what is the difference between macro and micro in terms of number of vehicles? Which one is for one vehicle? Micro is for one vehicle. Macro is for group of vehicles, right? Now group of vehicles will have the same speed?
No.
No, their speeds will be different. Okay, so to make it macro, I have to take their mean. Okay, so we are talking about mean speed. Mean speed can be of two types: time mean speed, space mean speed. Okay, you can take mean speed of two types: time mean speed, space mean speed. Okay, and the difference is which values you are taking for speed. The difference between them is which values you are taking for speed. Okay, if you look at the definition, they are almost same. Time mean speed of vehicles, space mean speed of vehicles. A specific time period, a specific time period. Okay, so in both cases, you go on the highway and you collect speed data for a specific time. You will have lots of values. You come and take their mean. In both cases, what is the difference? In time mean speed, the speed you will observe will be over a point or a lane. Okay, the observed speed for time mean speed should be over a point or lane. For space mean speed, it should be over a given section. Okay, so you put a device on a lane, there are some devices which you put under the pavement, there are some devices which you install on the side of the road. You have speed cameras, speed radars, and so on and so forth. Okay, so usually they measure speed over a point or a lane. Okay, for a segment, you have to observe the vehicle from one point to the other point, from start to end, whole. Okay, so for space mean speed, you have to take the speed of the vehicle from the start till the end, the average speed of one vehicle from the start till the end. Got it? Now from start till the end, that means it's not a point, right? It's an entire length. Okay, and in this entire length, you will not be in one lane. Will not be in one lane, right? The drivers may change the lane. Okay, and when they change the lane, their speed could also change. Okay, so the space mean speed takes into account this variation as well. Time mean speed, it does not take into account this same. Clear? Okay. This is their equations. TMS is time mean speed, SMS is space mean speed. Okay. D means the distance over which you are measuring the speed. T means the travel time of the vehicle to cover the distance, and N is the number of vehicles you observed. Okay, D is distance, T is time, and N is number of vehicles. Okay, now you can see here summation of D upon T, right? Summation of D upon T. D upon T means what? Speed. So if you have a device, a speed gun, a speed radar, a speed camera, the speed camera will not give you D and T, right? It will give you what? Speed. So you can replace it. Okay? You want to use speed here, right? That's why I put D upon T. So if you can get the value of speed without D and T, you put it here, no problem. Okay? So for TMS, this can be replaced. For SMS, you have to put distance and you have to put time. Okay, it should be used in this way. Okay, the equation should be used exactly as it is for SMS. Clear? Okay, so we have data of 6 vehicles. For every vehicle you have the distance constant, and for every vehicle you have the travel time. For this data we have to calculate the TMS and SMS both. Okay, now if I go here, for TMS I need to do D upon T for each vehicle, right? So I can do the summation. Okay, so give me D by T for each vehicle here. Yes, first one. Same. Feet per second, no problem. Okay, next. Next. Mm-hmm.
52.6.
Okay.
0.6.
6 or 6?
6.
Okay. Big mistake.
50.
Okay, now for TMS, you just take their average. Summation upon number. Okay, how much is TMS? Divide by 6. Yeah. Okay, now for SMS, I need to calculate this first. T upon n, summation of T upon n. Okay, basically the average of travel time. How much is that?
$19.83.
19.8. Okay, then SMS is the distance upon this. How much is it? Any problem, any question? Clear? I don't care. Do I care? Huh? I have +1 in the class, I don't care. And you are talking about plus 0.1. Come on. Okay, any other problem? Okay. Even if it's 0.1 in your grade, I don't care. Okay? So if you feel I will get an F because of 0.1, yes, you will get an F because of 0.1. Okay, now we calculated two values, right? For the same vehicles? Same vehicles, right? Same distance? Same travel times? Okay, so the values are also very close. Okay, the values are also very close to each other. Okay?
Almost will be very close.
No, because there are couple of things which we are skipping here. First of all, you can see we are using speed in feet per second. Normally we don't. Okay, but here this is not our purpose. Okay, we are not going to use it for design or something. So whatever it is. Secondly, there are some restrictions, some limits. For the distance, you can use for space mean speed or time mean speed. We are not covering it right now. Okay, we will cover it in the speed data chapter. Got it? Okay, so that's why they are not same, because you cannot use the same distance for this and this. Okay, but they can be very close to each other. If you are doing it for the same vehicles and for the same road, they can be very close to each other by chance. Okay, and you can see this is 0.6 and this is 0.4, right? Okay. However close they get, this one will always be slightly higher. TMS will always be slightly, more or less, higher, but on the higher side. TMS is always on the higher side. Okay. Maybe the difference is more, the difference is less. Here the difference is very low between them. Okay. In some other cases the difference could be more. Okay. But the TMS is always higher. Okay. The reason is TMS is supposed to give you the speed of the vehicle over a point. Okay. So this does not include acceleration or deceleration. And SMS is supposed to give you the speed over the entire segment. So over the entire segment, the speed does not remain constant, goes up and down. Okay. So SMS by default is more towards the average speed, and TMS by default is more towards the higher side of the speed, the top speed, the maximum speed. Okay. It's built into their equation. You don't have to do anything. Okay. You don't have to play with the numbers. The equations are designed in such a way, and this is showing it, that even if you take the same numbers, same distance, same cars, same time, even then the function of the equation is that it will be higher and this will be lower. Got it? Okay. And I told you the reason. The reason is there is acceleration deceleration effect in SMS, and TMS is not supposed to have it. Clear? Okay. But as I said, this is not a practical problem. This is just showing you the difference between the two values. Okay. Practically we don't do, okay, take the same values and calculate TMS and SMS. We don't do it. Okay. Okay. The third thing is density. Third macroscopic parameter is density. Okay. Now you know about density of material, right? Density of concrete, density of cement, steel, wood. Okay. Your own densities. So how do we define density? Mass over volume. Okay. Now traffic mass is made up of what? Traffic is made of vehicles. So instead of mass we will use vehicles. Okay. And we are not concerned about height and width and these things, right? So we will not take volume. We are only concerned about the segment. The segment has length. So instead of mass, vehicles. Instead of volume, length. So density is vehicles per unit length. Vehicles per unit length. And the length can be in miles or kilometers. Okay. Now, if I ask you to measure density, how will you do it? How do you measure density? Vehicles over? Which vehicles? Which vehicles? Huh?
Vehicle passing the segment.
Vehicle passing the segment is what? Volume. So, if you count number of vehicles, I'll say it's volume or flow. It will not call it density.
No, we take the flow over the distance.
Huh?
We take the flow over the distance. Flow without density.
It's vehicles per unit time per unit length, not density. It's still vehicles per unit time, right? You will tell me if we observe for 15 minutes and we got so many vehicles. So it's vehicles per time, and then you will divide by length. So it will become something else, not even density, not even volume, it's something else. Okay, then you can file a patent with your name. Then I introduce a new term in traffic engineering. Okay, got it? You can do this. Okay, but if you do this in the exam, I will give you 0. Okay. Density should be when vehicles are on the segment, not passing. Not passing. Okay, we are saying what? Number of vehicles on 1 kilometer. Number of vehicles in 1 mile. So they should be on the 1 mile. When you are counting it, they are already passing. When you said 300 vehicles, are these 300 vehicles in the segment? No, those 300 vehicles have gone. Okay, some of them reached home. Okay, got it? We want what? Number of vehicles on the length. Okay, so you can use some equipment to measure it. Okay, we have sensors to do it. You can take a picture, okay, from a drone or from a satellite. Okay, you can do this. Okay, if you do it in Bahrain, drone is illegal. Okay, and so you cannot do it. And you do it from a satellite, then you are Elon Musk, which you are not. Okay, so it's difficult to measure density. Okay, density is difficult to measure. So we use some equations to calculate density usually. Okay, measurement of density is difficult because vehicles do not remain stationary on the segment. If all of them are standing and you keep on counting and they don't go anywhere, that's fine.
Can we use the one count in point and another one count in next point, and we subtract the number, so we got the number of vehicle and the segment.
How will you take one count from one point to another count? Same time?
Yes,
No, but when the vehicles pass, then you will count, right? When the vehicles pass, time has gone.
First point, the vehicle passed in the segment.
For example, you took the count for half an hour. First point.
Yeah.
Okay, and in the same half an hour, you take the count from the other point.
So one is gone.
Another person.
Yeah, maybe.
It's 1 kilometer.
Huh?
You only find vehicles for 1 kilometer.
Yeah, he's saying so. You do a count at 0 and you do a count at 1 kilometer. Half an hour here, half an hour here. Okay. Anyways, maybe I'll think about it. Maybe. Okay. But in any case, then you are counting in multiple locations. Still, it's difficult. Okay. So we usually use equations. Then we use equations. Okay. Now, why do we need density? If we have a road segment, 1 kilometer, 20 vehicles. We have another road segment, 1 kilometer, 100 vehicles. One has 20, the other one has 100. Okay, which one has more congestion, more traffic jam? The one which has more density, right? Which one will be slower? The same. Spacing between the vehicles. Which one will have more spacing between the vehicles?
Less.
The one which has less density, right? Okay. So density tells you all about all these things. Okay. And when the spacing is less between the vehicles, what about the speed?
Could be less.
Yes.
Speed will be lower as well. Okay. So density tells you about congestion. Density tells you about speed. Okay. Density also tells you about demand, right? If a road has more vehicles, it has more density and more demand. Okay. More demand as well, right? More demand, that's why there are more vehicles. Okay. So density tells you about the demand as well. And there are other parameters which you cannot measure. Okay. But you can have an idea about that, about those from density. For example, comfort of the drivers. If the spacing is less, you are going slowly, you are stuck in a traffic jam, you will more comfortable or less comfortable? Less comfortable. Sure, right? Huh? I have a friend who says I'm very comfortable then because I don't have anything to do. Huh? No, he is mad. Okay. He went on a break, now he came back. I will ask him again. Okay. But the comfort level is low, the freedom is also low, right? You cannot just change your lane whenever you want. Now, in reality we cannot measure these things. Freedom, comfort, convenience, these things cannot be measured, right? But from density you can have an idea about them. Okay, so that's why density is considered very important. Okay, now we move on to microscopic parameters. Okay, within microscopic parameters we already have seen one of them. Which one? Speed. These values, they are what? The speed of 1 vehicle. So these are microscopic. When you took the average, then it became macro. Okay, but these single values are micro. Individual values are micro. So this is already covered. Then we have a spacing. Okay, spacing is the distance between two vehicles. Okay. Now the only clarification here is when we hear the word spacing, we generally assume that it is this space. Okay, the clear space between the two vehicles. For us traffic engineers, okay, this is not the case. We measure it from a common reference. So it cannot be from the rear bumper to the front bumper or the rear tire to the front tire. Okay, it has to be from the front bumper to the front bumper. If you want to take it from the rear bumper, then to the rear bumper. If you want to take it from the tire, then to the tire. Got it? Okay. So what will happen? If I take it from front bumper to front bumper, the length of this vehicle is included. Got it? Okay. So this is a clarification here. Now, if you take spacing between two vehicles, you will have one value, right? Spacing between two other vehicles, same value? No. So for every pair of vehicles, I can have a different value, right? Okay. So these values are microscopic because each value is between two vehicles. So all these values are microscopic. Now you take all these values and take their mean. It becomes macro. Okay. Now, what are the units of spacing? Feet or meters. Feet or meters. Okay. Feet or meter per it is between what? Between two vehicles, right? So this is feet per vehicle. Feet per vehicle, right? After vehicle included, right? Okay, so it's feet or meter per vehicle. If you say 200 feet, so after 200 feet I have what? The next vehicle, right? So feet or meter per vehicle, distance per vehicle. And if you do the inverse, vehicle per distance, what is it? Vehicle per distance is density. So when you do the inverse of average spacing, then you get density. dA is what? Average spacing. Why average? Why not just take any value? Take this value. This is almost 9 meters.
Because the spacing is micro.
Yeah.
And
Okay.
the density is macro.
So you cannot mix
have
them.
to convert it.
Okay. So you always have to use average. Okay. Somebody took one value and put it here. The density will not be accurate. Okay, because density by nature is macro. Okay, so you have to make a spacing as macro as well. That means you have to take average. And what is this? What is this?
Constant factor. Constant factor.
No, it is
It's constant. It's constant, but factor for what? Safety. 5,200. No? Vehicles. Factor for what? It's written here. Length of the car is 5,280. Which car are you talking about?
You convert from feet to meter.
Feet to meter. 5,280. Feet to what? Yeah, it's conversion. But feet to meter. Come on. Feet to meter is 3.28. Kilometer. Very good. I'm telling it's written here.
2 mile times.
2 mile, come on.
2 miles.
It's written mile. Feet.
The time, say the answer.
Huh?
Say the answer, please.
Feet to, you said feet to meter. Mile, mile. Mile is not same as meter. Okay? So why? Because spacing cannot be in miles. Spacing between the cars cannot be in miles. You have one car here and the other one after 1 mile. Go home. There's no problem on the road. You are the only problem. Okay? And if it is, if that somebody says I will measure density in vehicle per feet, how many vehicles in 1 feet? Huh? Thanks for trying. Okay, but it's 0, right? It's almost 0. Okay, so we don't do this. So density has to be in miles and the spacing has to be in feet. So that's why we need the conversion factor, and that's why we have the other equation. If you are using spacing in meter and density in kilometer, vehicle per kilometer. Okay, and here you see, and you will see in other chapters as well, we always do the conversion in the same unit system. Okay, so feet and mile is one unit system. Okay, and meter and kilometer is one unit system. Then we have headway. Headway is same as the spacing, but in terms of time. Headway is in terms of time. Spacing was distance between two vehicles, same point. Okay, headway is time between two vehicles, same point. Time between two vehicles, same point. Okay, so for example, here the guy. Okay, let's say he is checking his notifications on the road, very dangerous. Okay, but the car passes him. Okay, and he starts counting the time. He starts a stopwatch. Okay, when this car passes the same point, he will note it down, and this time will be called as headway. Okay, and again the same issue that we had for spacing, it should be for common reference. So he started from front bumper, passing of front bumper, he should end with the passing of front bumper. Got it? Okay? Now the units of headway are? What are the units of headway?
Vehicle per feet per thing.
No. Huh? Yeah, say again. Second. Yeah, second per vehicle. Headway. Time between two vehicles, right? Second per vehicle. Okay. Now again, it's what? Microscopic, right? Headway is microscopic. Okay. So when you take single values, individual values between two cars or two vehicles, it is micro. But if you take many values and you take their average, it becomes macro. Okay. And the units are time per vehicle, right? Time per vehicle. And if you take the inverse, it becomes vehicle per time. Vehicle per time, we called it what? Vehicle per unit time. Vehicle per time is distance. Vehicle per unit time. Flow. Okay. Vehicle per unit time is what? Flow or rate of flow. Okay. So like we did for spacing, we can do the same thing with headway as well. But still you have to take average headway because flow rate is macroscopic. So if you take the inverse of average headway, it becomes rate of flow. Okay, and this is very easy. Factor for feet to meter, huh? Feet to meter, seconds to hour, huh? Seconds to hour. Okay, last thing. In this course, we will be discussing the macroscopic parameter, volume, speed, density. Okay. Even in the other courses, any book, any course which is related to traffic, design, engineering, management, they focus more on volume, speed, and density. Okay. But where is the use of microscopic? We will not use them very often, but just to give you an idea. One use of microscopic parameter I already showed you in the previous slides, which was what? If you have headways, you can do what? You can find flow rate. If you have a spacing, you can find Density. Okay, so one use is use micro to find macro. Got it? This is one of the uses. Okay, and to complete that, you can use headway and spacing both to find out speed. Okay, this is space mean speed, by the way. Space mean speed. Okay, this is what average spacing, distance. This is what average, average headway, time. Distance upon time equals speed. And this is the conversion factor. If you want speed in miles per hour, if you want speed in kilometers per hour. If you want in miles per hour, the spacing will be in, if your spacing is in miles, feet, okay? And if you want in kilometers per hour, the spacing is in meter, okay? And the headway is in
No. Second.
second and second.
Second as well.
Yeah, obviously. Okay, this is a good thing about time, it doesn't change. Seconds, obviously. If it's 1 hour, then you will wait for 1 hour for the next car to come. Okay, so these are the conversion factors, but as I said, conversion in the same unit system. Okay, another use, the last thing, another use of microscopic parameter is to focus on individual vehicles and individual drivers. I want to see the behavior of trucks on the road. Or let's say we introduce automated vehicles, driverless vehicles on the roads. We want to see how they are behaving on the road. So I will not use macroscopic because macroscopic is combined, both, all of them. Okay, I will use microscopic parameters of those cars and trucks and drivers. Okay, I will use speed of those cars, headway and spacing for those cars and drivers. Okay, because if you take macro and you give me, for example, space mean speed, this space mean speed are for all the cars. Okay, so in order to differentiate between them, you have to take their microscopic parameters. Got it? Okay, so one application was to find out macroscopic parameters, and the other application is to see the behavior of a specific type of drivers or